to be honest, I can't recall what they all are. They should be here somewhere on iTunes. Let's see if it knows. But that's probably a good idea to have podcasts of these classes, and then it becomes a lecture, you get a live show. Also, what many podcasts have are secondary podcasts, where people discuss the podcast and just listen to it. So that you just broadcast. So we should try to organize that. That'll probably get people to pay to come to class. Or you're already paying, I guess. I can tell you. Let's see. Blacklisted or backlisted. Sounds bad, but it's really just about books. Face the Nation. It's a new show, Frank Skinner show. Oh, that's excellent. If you like British comedy, you should listen to Frank Skinner. I know this has nothing to do with your lecture. I'll get to it soon. There's Friday Night Comedy. I wasn't lying. Hamish and Andy, I detest. They're two Australians, and I do follow Australian comedy, but they're not the best. There just aren't any good Australian podcasts. History of Rome. I stopped listening to that, and that's not a history book. It's the whole history of Rome in 2,000 episodes, taking it year by year. Very interesting, actually. In Our Time, that's quite good. Invisibilia, that's off now. Ken Rudin, Rachel Maddow, a little bit of a lefty. Mystery Show, dead. Nightly News, of course. No Such Thing as a Fish. Nothing computer science. I am so ashamed. But there are good computer science podcasts. It's just, I've got a big roster. I mean, I don't have any more hours in the day. I literally listen 24 hours. I listen while I sleep. I put on the boring episodes and just listen through them. Well, you probably don't have time to listen to podcasts, but it's a good idea. You can actually learn quite a lot. So let's get back to the real life and what we have to do. So on Monday, we implemented put. And to put a key in a value, to associate a key in a value, I said I'm going to use my internal routine called insert, which will insert this key and value pairing into the tree that starts tree, the node or tree. In fact, looking back, it's a very bad name for the variable because I don't want to say that in class all the time. But you can imagine that each node is the root of its little subtree. It is the root, and all its subtrees are below it. And it may be a subtree of a different tree, so every node actually corresponds to a tree. So it makes sense in that sense. But let's call it, oh, can't inline, I want to rename actually. Let's call it N. Let's call it NN, because that's nice and clear. So I'm inserting the key and value association in the tree that's rooted at node NN. And if NN is null, there's no tree in existence, so then I make a new one and I send it back. So this routine is always going to send back the new tree. And I'm repeating myself, but just want it to be clear. And let's face it, you students only hear 10% of what I say in class. I said 10% of what I say in class, and I only remember 10% of that. So it's only 1% that I actually can tell you. Unless I've done it 100 times, which actually it's not to do. If that tree is not null, it already exists, then I must check. Do a comparison between the key of the one I want to insert and the key that's already in the node, nn.key. If R is 0, so that key comparison returns to 0, which means they're equal. I'm trying to insert a key and a value, and the key is exactly the same as the key that's already stored in this node, nn. So then I replace the value. Simply say nn.value equals value, and I'll return nn, which is the new tree that I've constructed. It still will remain the same. The only thing that's changed about this tree is the fact that nn's value has been updated. Why has it been updated? Because the key that I'm trying to insert is the key of nn. And otherwise I do other things. Why do I need to return nn if all I'm doing is updating its value? Because whoever called me passed nn to me. I have a reference to nn. If I update the value, that reference will stay pointing to nn, and I don't need to return nn in this case. So why return it at all? Well, the fact is, this returning the new tree that I've constructed is really only so I can do this little trick. So that when nn is null, I can make the new tree and send it back. If I couldn't do that, or if I didn't do that, if I did it some other way, there would be no need to return in down here. I'm sure the book has a lot more about symbol trees. Symbol tables, binary search trees, sorry. Let's just see what they have. Let's do that. It's a little small, but it's fine, we can still see. So they're talking about inserting, and they're actually working through an example of how you insert, what does a tree look like. One thing which you should know is that even though I said that we can achieve log-n performance of binary search tree if it's balanced, which corresponds to a sorted array doing binary search in a sorted array. If it's balanced, we can do log-n. Operations will cost log-n time. And that's true for looking up keys and for inserting new keys. And, well, we only have 3 operations. Get, contains, are both looking up and inserting, put. So I said that the cost of those 3 operations will all be log-n if this tree is balanced. And I said that you can easily make a balanced tree, but easy is relative. So in this course, we're not going to look at how you make a balanced tree. And even if the textbook talks about it, I'm not going to tell you. But think you know. Next year, you'll be spending a lot of time doing that. Balanced trees are really important in science. If you are using, have any of you ever heard of the internet? So it's this thing, and if you interact with it, you're interacting with a web server, and you're talking a certain language to the web server. What is that language called? HTTP, that's correct. That's the language that you're talking to the web server. And it sends you back a file that you show on your computer. That file is written in a different language called HTML. Good. And on the web server itself, many times it's using a different language to actually process that HTTP that you're talking to. So HTTP is a kind of a language that you communicate with. But when the web server is processing your request, sometimes it uses Java, sometimes it uses C, but these days, most of the time, it's using PHP, another programming language, which you ought to be able to pick up in a few weeks, in 2 weeks, because it's so similar to Java, and you know how to program, you know the concepts. What I really want to get at is that that PHP program, I mean, it's one thing to know a web page nicely and neatly, but a lot of the time, there's a lot of data involved. Where the web does the data come from? Let's just find a web page. Not this one. This one is static. Everything you see on screen here, all this detail, I mean, web browser is showing me the HTML, which is a description of this, what should appear on the screen. But I got this by talking to the web server using HTTP language. And that web server, it didn't actually use PHP to process this. These pages are not generated. They are static files. They're just HTML files stored on the web server. And it's not doing any processing. All it's doing is it's reading the PHP and sending it back one of those HTML files. So all these files are what we call static. But if we look at a dynamic web page, let's find something that's dynamic. Ooh, something that won't. Let's find this page. Oh, won't work because okay, it has to be local. So, well, let's just use Google. No, Google's not good. Just give me a second. I'm getting to my point. I know I've digressed a lot. Oh, let's go to the stupid sunburn. If I were to log in and look at any page, that page is not static. It's not stored somewhere fixed in its fixed form. It's actually generated on the fly. And it's generated by, there's a lot of courses, a lot of different data that can be filled in on the page. That data is retrieved from a database. So all the data is stored in a database, which is a special program that stores loads of data and can be manipulated quite quickly. You need to do that on the web. That database can only work because inside it has loads and loads of balanced trees. It holds many, many balanced trees. So balanced trees is the the foundation for all databases. And databases is responsible for most of the content on the web. Most of the content we see on the web is stored in databases. There's relatively little, there's much more dynamic content than static. So that's all a way of getting back to the fact that balanced trees are really important, but we're not interested in today. If we happen to have a balanced binary search tree, then we're very happy because the operations will be cheap. And performance characteristics. So we're really talking about the fact that if we're dealing with a tree that's nice and balanced like that, the left-hand side and the right-hand side have the same number of nodes, then it's fine. If we insert these in a random order, then we're likely to get such a balanced tree. If I take all the keys that are stored in this tree, of, it, times, best, the, was, worst. If I insert them in a random order in the tree, I will likely get a kind of balanced tree. And that's fine. The only issue is that what happens if I insert them in sorted order? Sometimes you have data that's already sorted, and you want to store it in a binary search tree. If I insert a key that is bigger than the previous key every single time, the tree will be constructed in the following way. It will make the first node, and then the next key that I want to store will come along, it will be bigger, and it will put on the right-hand side. That's fine. You know that the left subtree is for all the smaller keys, the right subtree is for all the larger keys. My root, I've just inserted my second item, which is larger. Now comes the next key, and because it's sorted, the next key is also larger than the last key I inserted. So it belongs to the right-hand side of the root and to the right-hand side of that child, and it goes to the right-hand side. And the next one also goes down the right, and I end up with a tree that looks like this. Best, it, of, the, times, was, worst. Now, it's a kind of binary search tree because it's binary, even though all these left pointers, left references, left children are null, so empty trees. It's a binary search tree in the sense that left is smaller, everything on the left is smaller than everything on the right, and best is in the middle. But unfortunately, there is never anything on the left. So I end up with something that's basically a linked list. If I insert my keys in the worst possible order, I end up with a linked list. And for a linked list, you know that the performance, all operations cost order n time. So at one extreme, I've got order n time, if everything is unsorted, and I've got a linked list basically. And the other extreme, I've got a perfectly balanced binary tree, and the cost is log n. So we want to kind of avoid this. We also want to avoid, I mean, this is another ordering that's bad. So if I have my sorted array, I insert the first, then the last, and the second, and the second last, and the third, and the third last. That won't help at all, because I'll get this. That's the first best. Next comes worst, so it goes on the right. Next comes it, which is larger than best. It's the second largest, because I picked it that way. But it's less than worst, so it'll come there. Then comes was. Was is second largest. Did I just say? Anyway, was the second largest. So it's larger than the least, but it's less than worst, so it goes this side, and it's more than it, so it goes that side. This is no better, even though it does alternate left and right. It's no better ordering than sorted. So you kind of have to be careful, and that's why we want eventually to implement balanced trees. You do that with various special ways. Okay, then I talk about reversing a BST. This is kind of important. Just want to check that. Okay, fine. So that's all we have to do, really. All we have to do is to talk about reversing the tree. How do I, if I want to iterate over all the items in the tree, how can I do that? There are only three ways. Well, let's say there are three natural ways. One way is to say that I need to write an iterator, so I start at a node. And I'm supposed to send back all the items in the tree that's in this rooted at this node. So I've got three choices. Either I can say, I can call myself recursively. So let's iterate over my left subtree, and it'll send back all the keys that are stored in the left subtree. Then I iterate over myself, meaning I send back my own key. And then I iterate over all the nodes in my right subtree. So I've got all the keys in the left, I do myself my own key, all the keys on the right. That is called in order, because I am in the order of the smaller ones, then me, then all the larger ones. I could have done things differently. I could have said, I will send back my own key first, and then all the ones on the left, and then all the ones on the right. That is called pre-order. I ordered myself before all the other keys. And oftentimes that's really, really useful. And the last option is to say, I'm going to do post order, which means I'm going to call myself recursively to send back all the keys in my left subtree, all the keys in my right subtree, and then I'll send back myself. I come last, I come post the others. Obviously that's called post order. So here they've got a little routine called traverse. Let's just see which ordering it uses. So it's called traverse. It takes a node X. Oops. If X is null, it doesn't do anything because this is an empty tree. It should not send back anything. Then traverse calls itself on the left subtree. So first it's going to do the left subtree. Then it does a standard out print line of x.key, so the key of me, x's key. And then it does traverse x.right, so all the keys on the right. So this is in order. If I first do all the smaller ones, then I do myself, and then I do all the larger ones. And for each key, I print it out on the standard output. What will be the ordering of the keys on the command line? You read all the sort, don't you? Because first ones all come all the small ones, then the next one, and then all the ones that are larger than the next one. And for each subtree, they do the same thing. So this is a way of sorting numbers. Binary search trees is another way of sorting numbers. Let's see if we can actually implement this, because I can see that you don't believe me. What is this? So this is BSTST, binary search tree symbol table, and it's associating keys and values. But I just want to sort. I want the keys to be sorted, and I don't care about the values. But I'm still going to use this because I've written the code. I don't want to waste it. So I'm going to write a new class called sort, BST. And I'm going to write a main. And I'll need a BST, BSTST. And I need to say, what am I going to map to what? So I'm interested in the keys, and for the sake of simplicity, let's sort words. So I'm going to map strings to what? I don't care. You can put anything here. I'm just going to say string. This is my binary search tree. I'm going to say I want, okay, oh. Okay, let's just click this quickly. I kind of made it's not a bad mistake, but it's kind of a mistake. I said, make a new binary search tree symbol table that maps strings. Yes, that's what we want, to strings, don't care about that. I put the open bracket, close bracket afterwards because it's constructed. Normally I would write this. Make a new instance of class BSTS, but remember it's generic, it's parameterized. So Java will complain, and actually it'll infer type arguments, whatever. It's clever enough to fill in its string to string, because it knows that it's string to string. Okay, right. So this part is fine. This part is not so hard, because I said that one of the great things is that when we're using a symbol table and using interfaces, we don't need to really know exactly how it's implemented. We can use a symbol table by simply saying ST, EST. And if I wanted to, I can change the implementation here on this side later on. I can say there should be an array symbol table or what have you. But I'm not really interested in using BST as a symbol table. That's why the second string doesn't matter. I really only want the capability that binary search trees give me of being able to sort. So if this is a generic symbol table, it doesn't really help me much. I'm going to say that this is I know that this is a binary search tree symbol table. I'm going to actually ignore the fact that it's a symbol table. I'm going to use the fact that it's a binary search tree. That's what I'm really after. I've written the code. I'm not going to rewrite it. Right. Then we insert a few things. So put. Now we need names that are, or words, strings, that are not sorted because I want them to be sorted soon. So what phrase shall we use? Any suggestions? Okay, I'll just write a sentence. I just love, oh no. Computer science. And just to make sure, let's just put a dummy A in there and just a dummy ZZZ. Just to make sure that it actually is sorted. Otherwise, it looks real cool. Okay? And now I want them to be sorted. How do I do that? Well, what we did in the stacks and queues chapter is to write an iterator. I haven't written the iterator yet. I'm too lazy to do it now. So I'm going to say BST traverse. Now, let's not call it traverse because it's put dump. When you walk through each node in the binary search tree or any kind of tree, that's called traversal. You know what traverse means? To walk across, walk over. It's called traversal. And I could call this routine traversal, but that's very generic. And I'd rather call it something that's more specific like dump, which will just dump it on the screen. Unfortunately, BST has no method called dump, so I need to add that. Let's just consider that for a second. Can I add it? I said that a BSTST implements a symbol table. Am I allowed to add a new method to BSTST that's not in symbol table? Well, yes, I am. Implements ST key value only means that I promise to obey the contract that symbol table specifies, and I can do more if I want, but I can do at least what ST key value promises that I will be able to do. So you're welcome to add new things to this class. I'm going to add dump. Okay, I need to figure out what dump is going to do. One small issue before I carry on. I see that I have override here, add override. Have you learned about that in this course? Yes, you did, but you can't call a fucking thing about it. Don't know. Okay, let's take a victim. Victims come from this one. Actually, I shouldn't do that. No. Victims should come from here. Because, well, this comes to empty. I'm honest. Because these are the people who can see the screen least to best. Let's get up first. Okay. Sign off. Well, let's add override.
What's going to override the standard method that Java includes itself?
Java doesn't have a get method. Does it?
Or would override the method in the interface? Well, not the interface, in the standard class.
What's standard class? Which one? Tell me its name. Okay, right. So override is a signal to Java, to the compiler. That says, here comes the implementation of a method. In this case, get with the signature. It returns a value, it takes one parameter called key, This is the signature of the method. Override is a signal to Java that says, I'm going to write the following method. And I know that it's already defined somewhere else. Either in my superclass, does this have a superclass? Yes. Class BST, does it have a superclass? Take question. 20 marks in exam.
Object.
Yes, it does have a superclass, even though it's not specified here. There is always an implicit superclass object. Does object have a get method? Gee, I don't know. Let's just double check because it may just have. Where is object? I'd love to think there are exciting and exotic protests going on outside, but I suspect it's a lot of workers digging that trench. What are they doing? They're probably laying a pipe. But where to? That's what's bothering me. Where is it going? And what are they putting in the pipe? Object. Must be here somewhere. Object. Oh, there we go. Java lang object. What does it have? Oh, it has loads of stuff. Clone equals finalize. What the hell is all this stuff? But no get. So object does not have a get. And even though it's not mentioned, BSTST is actually an extension of object. It's implicit. So I'm not overriding object's method, get, because it doesn't have one. But I'm also implementing this ST interface, and that does have a get method. And that's what I'm signaling to Java that I'm overriding. So I'm actually specifying this method now. I'm signaling to Java that it's overriding the get method in, and Java knows that it's ST. What happens if I take away, second Victor, what's your name again? David. David. Exactly. Damien, what will happen if I take away override? What will the error be?
I'm not sure exactly.
It does, but you can write it yourself. It's not illegal. You can just take it away.
Yeah.
In fact, if you don't have chips, it won't be auto-generated anything. You have to override yourself. What will the error be when you take it away? This is also a trick question. 20 marks, for example. 20 out of 2,000 marks, for example. What error will Java report, Java compiler report if I take away override? Okay, let's save first. No errors in BSTST. Take it away, save. Oh my God, there's no error. So Java doesn't care about overrides. If you take my all out, it just won't care. So what's the use? Well, the use is there to protect you. I'm a little programmer. I know that I have to implement get because I promised that in the interface. So I say, okay, I'm going to write my get. I'm going to override it. And nothing complains. So that means, yeah, you're overriding the get method. Then my very stupid twin brother comes along and says, here's dump. And that's also overriding a method. I'll just put override in the front and I'll just, And now Java's complaining. Because I thought I was overriding dump. But the Java compiler, through Eclipse, the Java compiler says the method dump of type whatever, that's a signature. Sorry, that's a class content, must override or implement a super type method. Aha! So I thought I was overriding dump, but there is no dump to override. So override is a kind of protection that I always add so that I'm always aware if I think I'm overriding something, but I'm not actually. I'm going to take override away. Oh man, I thought I was 20 minutes or something. How do I implement dump? I need to dump this tree. The one that's represented by this BSTST, binary search tree. So where do I start? I start at the root. What do I do with the root? This is kind of tricky to explain. Let me write the answer and see if that explains anything. I'm going to write my own routine root that's internal. This one's public, and it's the one that I'm going to call from sort BST. There it is. But inside, I'm going to add a private dump that says dump the tree that starts at node NN. I don't want the outside world to know that I have a root. Root is private. Nobody needs to know that this binary search tree has a root. In fact, it may have several roots. It may kind of like keep old roots around for whatever reason, or it may not have any root and somehow list the nodes in a different way. It may store the nodes in an array of some kind. Who knows? Bottom line is that root is a private thing. The outside world that calls dump does not need to know I have a root. But inside, I have to start somewhere in the tree. It doesn't make to start dumping in the tree. It's at the root. There we go. And all I need now is to implement dump. And we'll do an in-order traversal because we want to check that it creates a sorted list. So I'm going to say if NN is null, then I could just return as I did in the textbook. But I'm going to actually say something else. If NN is not null, dump its left-hand side. In dot left, dump in dot left. I'm going to dump myself, and I'm going to dump the right-hand side of NN. So I know in the book textbook they have if NN is null return, which is basically what this code will do. If NN is null, nothing will happen. But if NN is not null, I'm going to dump my left-hand side, all the smaller nodes. I'm going to print out my own key, and I'm going to dump the right-hand side, all the larger nodes. Don't think I need anything else. Sort BST is happy. And if I run this, I should get the output that lists all these words in order, which would be R, computer, I just love science, Z. Computer, I just love science. That's what it's going to print. How appropriate. I should have prepared by making a sentence that you can say in different ways. Oh, save. Yeah, what? Save it. I don't care. Errors. Yeah, but I'm not going to use any of them, so it's fine. You can proceed. And it's printing computer, I just love science in alphabetical order. So this is exactly what I expect, and this is a test of my binary search tree. Of course, I could have had errors in the binary search tree. I may still have errors in the binary search tree. There may be bugs. So we don't know that there isn't some mistake in my binary search tree. I need to write many more little tests, just like these, to make sure my binary search tree is wrong, is correct, not wrong, to make sure it's wrong. To make sure it's wrong, I have to write. When you implement binary search trees next year and you implement balanced trees, it's quite tricky because what you have to do is something called rotations. If the trees are balanced, you have to kind of rotate it a little bit. And then you rotate to rotate, and what you do is you color them in colors as well. If you're in the green node, you go to the red grandparent and you rotate that one, and then you go to the uncle, blue uncle, and you rotate again. All kinds of various stories. In fact, there are many ways of implementing balanced trees. There's something called a red-black tree. There's a red-black-white tree, I think. There are AVL trees. I can't really list all of them. D trees, we like those. Bottom line is that next year you'll be implementing some of the stuff. You will make mistakes. It's really critical that you implement tests to make sure your binary search tree is working. But here is at least one very simple test. Okie dokie. Let's just see. What else do we need to talk about? Nothing really. I think that's about it. So just before I never see you again, or I may be seeing you next year, who knows. Who could program before they started doing computer science? Don't be shy, Megan. Oh, it's not. So you guys just told, okay, people who could not program, just raise your hands. Okay. Who of you did the bridging course? So drop your hand if you did not do the bridging course. You couldn't program, you did the bridging course.
Yeah.
Okay. Excellent. Sample of 1. Oh, 2. Can you program now?
I think so.
A little bit. Can you program now? No. 0. Okay. Did the bridging course help? Okay. Did this course help?
Yeah.
I guess so, because otherwise you would just have the bridging course. It's 5 days. And I hope we can't squeeze this whole course into 5 days. Okay. The people who did pre-programming at school, who could program before you came to university, was it difficult this course? Very? Okay. Medium?
It was super, really, really easy, and then one day you passed the school syllabus, and then we were kind of chillaxing and not really focusing on much shit. And we got ahead of it.
So how do we fix that? Because that is a real danger.
I think it's all the students' problem.
Yeah, how do we fix the students? So what they do at other universities is to, from day 1, program in a way that no one has ever seen before. So they usually start with functional languages, which is something that you haven't done at school and that everyone's in the dark about. I think that's going to work here. So I don't know how to fix this issue really. Oh well, never mind. People who could not program and did not do the bridging course. Excellent. 5 samples. Let's start with the class of 8. Hard, easy. Hard compared to maths. Really? Maths was easier. Did you do maths at school? That gave you a distinct advantage, I feel. The fact that you could count before, I mean, that's like being able to write if statements at least. Who else? Could not program, no bridge course, can program now. Hard or easy, this course? Wasn't easy. So you are saying the course is very hard, you're saying the course is super easy up to the crash. So it's very difficult to fix this course correctly. But we have to do something because next year we are going to have about double the class, I think. So we're going to have loads of BCom students coming because we've added an extra course. So somehow we have to figure out something. One thing that does help is to, who's carrying out of computer science? All of you, that's excellent. Just one little holder. One little holder. Okay, fine. One thing that does help us next year to teach is having good demos. One thing that will help you, if you carry on with computer science, to learn to program, is to be a demo. It's almost no money. In fact, you have to probably pay to be a demo a little bit. Because you could have earned money. So you're losing money. You're not losing money, but it's very little money. It's like, I don't know, about $2,000 a semester. That's not a lot of money. But the value of being a demo is that by trying to help other students, even though you think you know nothing, or as little as they do, they don't know that, you can bullshit them, and you actually do learn a lot about whatever subject you're demoing. So if you're all interested, please volunteer to be demis for Computer Science 1 next year. You'll get an email pretty soon. We'll start to get desperate and saying what happened or something like that. Please say yes if you want to learn to program well. People who are demis do better because they learn the work more. But this is also true for other subjects. So if you feel you're worse at computer science, you don't need to learn to program even better, but you suck at physics, you are going to take physics next year, volunteer to be a demi for physics, because that's one sure way of actually learning the material. Okay, just one little tip. And I'm going to stop. Thank you very much.